Welcome back to Cloud 42, I'm James. Today we're continuing work on the Toolpost grinder. This is going to be part 15. If you haven't seen the other parts of the series, there's a link to a playlist down in the description. Now last time we were working on the AXA Toolpost clamp and we got it mostly finished. The only thing we have left to do is the height adjuster wheel. Now the height adjuster is a relatively simple piece of turning, but the outside of it is knurled. And knurling is something that a lot of people have trouble with, so we're going to take a little bit closer look. Let's go over to the bench and look at the plans. This is the height adjuster, and as you can see here in the drawing, it's just a metal disc with a threaded hole punched through it, and then we're going to knurl the outside. Now, the dimension I have shown here on the plans is 875 thousandths, and that is just the same diameter as the height adjusters that are on my other AXA Toolpost tool holders. Now, because we're going to knurl this, we are going to have to adjust the outside diameter to get a proper knurl. This is my knurling tool, and this is just an inexpensive bump knurl with two wheels, one each direction, so you get a diamond pattern. And this is what's called a 16 pitch knurl. It's an imperial knurl, and the 16 pitch just means that there are 16 teeth per inch on the knurl. So the width from one peak to the next peak of the knurl should be 62.5 thousandths, because that's 1/16 of an inch. Now if we want a clean knurl around the part, the circumference of the part has to be an exact multiple of that 1/16 of an inch. Now this is a part that I knurled about a year ago. This is part of my camera support rig. And you can see that the knurl on this is very fine, much finer than the 1/16 of an inch of this knurling tool. But I actually did make it with this knurling tool, and what happened is the knurl double tracked. I didn't pay any attention to the diameter, and I just tried it to see what would happen. And the knurl actually double tracked because the circumference of this part is not an exact multiple of a 1/16 of an inch. It's actually got an extra half of a 1/16 in there. Let me show you what I mean. Let's do some math. The outside diameter of this part before knurling was about 1.2 inches. So if we assume that we're trying to get an even number of teeth around so that as the knurl rolls around the outside of this, or as this rolls against the knurl, forming teeth every 1/16 of an inch, if we want the teeth to line back up in the same grooves as they come around, then the outside circumference of this has to be an exact multiple of a 1/16 of an inch. So the formula to figure out the circumference around a round part is just the diameter times pi. So in this case, it was 1.2 inches times pi, 3.14159. That's plenty. So this is the circumference around the outside of this part is 3.7699 inches. Now, if we just divide that by a 1/16 of an inch, divide it by 0.0625, then we get 60.32. So what's going on here is we do not have an even multiple. There's actually about an extra third in there, and the way it works out, it turns out as the knurl starts to make a dent and then the next tooth comes around to land in that, if it's slightly misaligned, it'll go ahead and just follow that down. So this 60.3 is close enough to 60.5 that as the knurl comes around and it doesn't line up in the same groove, it ends up off by half a groove and making a new groove in between. And then when it comes around again, it's off by another half a groove and it lands back in the original. So what we get is a double tracked knurl that ends up being half the pitch of the tool that made it. Now, I actually played around yesterday a little bit with some steel, trying to figure out how this knurl works, because I haven't used it very much. Just trying to play with it. And I did get it to track, but I'm really not happy with it. It's a little bit coarse. It's very rough. I don't like the feel of it. I actually like this double track knurl. So let's see if we can reproduce that when we make the height adjuster here. Now, the original dimension here, 0.875, let's see how that lines up with our 16 pitch knurl. So 0.8 0.875, multiply that by pi, times 3.14159. So that's the circumference. Divide that by the pitch, 0.0625. And you see that's 43.98. So that's just as close as you're going to get to 44. So that is an even multiple of a 1/16 of an inch. So with a 0.875 diameter part, we should get a properly tracking knurl. I don't want that. I want to actually hit it in between. So we can either go up or down. So this is 44. I'd like to go a little bit larger. So let's say 44.5 is what we want. So if we want 44.5 teeth around it, we can just say 44.5 and then multiply that by the tooth size, 0.0625, and that's the circumference that we want to hit. Well, since the circumference is just the diameter times pi, we can divide by pi and see what diameter we need for the part. So divide that by pi, 3.14159, and that says we need 885 thousandths. So let me make a note of that. And let's go over the lathe, make this 885 thousandths and see how the knurl tracks. Now here's the stock we're going to use. This is a 1-inch diameter piece of 1018 cold finish steel. And I'm going to chuck it up here with about 1 inch sticking out. We'd like this to be rigid because we are using a bump knurl, and they put a lot of pressure on the part. Okay, we're going to run the lathe here at 2400 RPM. That looks good. Let's start by facing the end. Okay, I can live with that surface finish. Let's take a cut on the outside, maybe 10 thousandths just to get under the skin, then we can take a measurement. That's 5 thousandths per revolution feed rate, which is fast at 2400 RPM. Okay, let's see where we are. Looks like we are at 986. And we're trying to go to 885, which means we have 101 thousandths to take, which is 50 thousandths per side. So we'll start by taking 25. Let's see where that gets us. Looks like we're about 930 and a half. Again, going to 885 means we've got 45.5 thousandths to go, which is 22.7 per side. So let's take 10, 20, let's try to dial right to it. Carbide leaves a beautiful surface finish when you run it that fast. Looks like we're about 886. I'm going to call that close enough. Okay, let me grab the knurl. Now the most important thing with a knurl like this is to make sure that it is actually on center. And you can do that by just feeding it in and watching when the wheels start to turn. So there I've got the top wheel turning and the bottom not quite, so I need to raise it slightly. Now the bottom's hitting first. Means it needs to be lowered. Okay, that's pretty close. Now what I'm going to do here to make sure we get a good bite and get plenty of oil on this, in fact, let me get some oil. This is just rapid tap. It's what my local supplier had in stock. Okay, there we go. Plenty of oil on here. Now what I'm going to do is I'm not going to run this at 2400 RPM. Let's run this all the way down as slow as the lathe will go at 150. Okay, now I'm just going to run this in by hand until I see the wheels making contact. Both wheels are making contact. Now I want to make a solid first impression to make sure that they track correctly. So I'm going to take 15 thousandths on the cross slide. Now that's not really going to push this 15 thousandths in, it's just going to put a bunch of pressure on it. In fact, I think I'm going to take it all the way up to 20. And then I'm going to start it and we're going to run it around. Actually, I could probably just do this by hand and see if we're tracking. Or more precisely, double tracking. And we are, that's actually what we want. I'm going to take another 5, make that just a little bit deeper. To make sure we're getting a clean double track. Yep. And then I'll turn it on and I'll feed it across by hand. This way we're not trying to cut the full depth on the full width of the knurl. Now bring it back out here, take another 5, bring it back across. Bring it out here, take another 5. Let's see how we're looking. Okay, we got a good double track knurl going, and we just need to take it down a little deeper. Again, I'm not going to try to feed in across the entire width. Take another 5 there. Another 5. Again, I'm under no illusion that this is feeding in 5 thousandths at a time. It's just adding pressure. We pretty much just need to take this until I'm happy with the depth. looks pretty good. Let's see, how much knurl do we actually have? Got a little over 200 thousandths. And I'm actually pretty happy with the depth there, so I'm going to call it done. I'm just going to spin it up and back it out. Okay, I can live with that. Okay, now that the knurling's done and we're happy with that, now let's go ahead and knock a hole in it. Grab a drill chuck. Now I'm going to start with a center drill just because it's rigid and it'll put the hole on center. Hence the name. Now I'm not pushing it in very far, and I'm definitely not drilling the whole tip into it. I'm just using the very point of the drill to make a depression that the other drills are going to follow. Now I'm going to pilot drill this because this is going to be a 3/8 inch thread, so it's a letter Q drill, which is pretty good size. Not really a problem, but I'm going to pilot drill it just to take some of the pressure off. Okay, that is wandering all over the place. Not sure what's going on there. I have a chip in there or something? Let's come back and make a little bit larger depression here. See if we can figure out what's happening here. There we go, that's better. Now we don't have to go that deep for the final part, but we're going to tap it, and it's a plug tap, so it's got some partial threads, and I want to be sure we can go deep enough to get full threads through the entire part. Okay, this is a letter Q drill. This is tap size for 3/8 24, which is what we're headed for here. that's the end of our pilot. We'll call that good unless we can't get it tapped. Okay, this is a 3/8 24 spiral point plug tab. And I'm just gonna feed this by hand until it slips. And we'll run back in there again just because it's a spiral point and pushes the threads ahead, pushes the swarf ahead. Okay. The next thing we need to do is clean up the end of the thread and put a little chamfer on this outside edge, and then we'll be ready to part it off. So to clean up the thread, I'm just going to use this. It's a little Noga rotary countersink, and just put a tiny little bevel on that front edge. And then to clean up the edge of the hole here, or edge of the burr of the knurl, I'm just going to use a chamfering bit here. Make sure I'm getting the whole edge of it off. That's 15 thou, that's 20. Yep. That's going to be nice. And now let's part it off. Just because we had all that pressure with the knurl, I'm going to check this. Make sure it's square. And let's part off a little more than the 200 thousandths we need. Try with the tool post locked. Okay, before we go all the way through, let me put a little piece of welding rod in the tail tailstock here. Catch it when it falls off. Okay, there we go. Okay, let me get some of this stuff out of the way here. Okay, the next thing we need to do with this is we need to face off the side that we just parted, get it to thickness, and put a chamfer on that side as well. And holding this, something like this flat in a 3-jaw chuck is a challenge. So we're going to use a lathe spider. This is just, you've seen this before. This is just a 3/4 inch thick aluminum plate with cutouts for the chuck jaws and 3 jack screws that allow it to be leveled. Now, I'm going to grip on this, and I am going to grip it on the knurled surface, but I'm not going to grip it very tightly. Just enough to hold it. Hopefully not enough to deform it very much. Okay, and we want to run a lot faster so we can get a decent surface finish on this. Okay, now the actual thickness of this isn't that important, but let's just see where we are. Still just a touch over 200. Let's take a little bit more. And there we're maybe 15, 20 thousandths over, and that is going to be just fine. So let me put the chamfer in. Now this is extremely close to the chuck jaws, so what I'm going to do is I'm going to come out here and I'm actually going to touch the jaw and then pull off of it slightly. I'm going to do a little spin, make sure we're okay, and then I'm just going to feed in with the cross slide. There's first point of contact, 5, 10, 15. Let's see what that looks like. See if that looks the same as the other side. Yeah, I'm happy with that. Okay, and we just need to clean up the inside edge. And that is that. I'm going to go ahead and just run the tap through it again by hand just to make sure we don't have any lingering partial threads or mangled threads on the edges. No, that looks great. Okay, well, let's go over to the bench and put it together. That is the height adjuster done. Double track knurl turned out great. The surface finish on the edges are good. The threads are nice and tight. Let's put it together. So this is the tool post holder, and we've got the stud already in here. And remember, the threads in here are tight, so this is more or less a jam fit bottomed in the hole. Height adjuster goes right on, and it spins freely. There's very little rock, and that's because we use an H3 limit tap, so this is nice and tight good clean fit on the threads. Now, of course, this spins freely, so in order to keep it from moving, we've got a wavy spring washer and a nut. And so this doesn't actually lock, we just turn it down to the point where it partially crushes that washer, and now you get a bunch of extra friction when you turn it. And so you just kind of keep the nut against it so you can still turn and adjust, but it keeps it from spinning freely. Just in case it wasn't abundantly clear, the purpose of the height adjustment wheel is to provide a stop so that every time this goes in the tool post holder, it ends up at the same height. So when this drops in, that wheel contacts the top surface of the dovetail so that then when I clamp it down, it's in the same position. So if this needs to go down, I turn the wheel to the left, it goes down, and then when I tighten it, it's in that position. And every time I bring it back, it ends up in that position. And if I need to raise it, turn it the other way, and it raises up and holds it in position. Every time I bring it back, it's repeatable. Okay, so where does that leave us? Well, we've got the grinding spindle done. We've got the motor clamp and eccentric done. We've got the pulleys done. And now we've got the tool post clamp done. At this point, we need a drawbar to go through the spindle to hold the wheels. We need some wheel arbors. And I think we need to think about a wheel guard for this. I've got some ideas for that, but that will have to wait for a future episode. If you're enjoying this series, please give me a thumbs up, comment, subscribe. Thank you for watching.